In the back of a transport truck somewhere in southern Africa, a lion rests inside a steel-reinforced crate. It doesn't roar, it doesn't move, it watches. Around it, every vibration, every shadow, every sudden noise carries the potential to trigger something primal. What few realize is that this moment, this silent, suspended moment, depends on a level of engineering precision comparable to what's used in moving radioactive materials. Because when the cargo can think, react, and attack, logistics becomes more than just transportation. It becomes containment science. Predator logistics doesn't begin with cages. It begins with control, not just of the animal, but of temperature, motion, light, and vibration. The same parameters managed when relocating nuclear fuel rods. The crates used to carry lions and leopards aren't just cages. They are mobile environments. Their walls are layered not only with reinforced alloy, but with acoustic insulators. Their joints are mounted on shock-dampening bushings. Their base plates are calibrated to absorb vertical and torsional stress. Every component has a single objective: to prevent a neurochemical avalanche inside a being designed to overpower anything in its path. Containment, in this context, becomes psychological as much as physical. The design of the crates mimics that of mobile nuclear vaults, with isolated chambers, zero exposure zones, and double-locking systems that function even under mechanical fatigue. The goal is not just to restrain, but to neutralize sensory stimuli. No reflections, no drafts, no echo. Even airflow is filtered and directed to avoid triggering the predator's highly sensitive olfactory system. It's not a prison. It's a carefully managed cocoon of environmental silence. The risk isn't visible. It doesn't wear a hazard label or emit light. It hides in what we can't see. The moment a truck hits a pothole, the hum of the engine grows irregular, or a human scent drifts too close to the bars. These are the invisible instabilities, like radiation leaks in a cracked seal, that can provoke fear, agitation, or sudden aggression. A predator under stress doesn't simply pace. Its adrenal system floods, muscles contract, decision-making vanishes. The containment must prevent that cascade before it begins. To understand this operation, imagine a comparison not with the jungle, but with an explosives cradle used in deep mining operations. In both cases, the cargo must not shift, must not rattle, must not feel threatened. A lion in motion is not just a majestic creature being relocated. It's a biomechanical system under constant psychological load. And to move it safely, human intelligence must predict what it will fear before it even knows it. This is not about domination. It's about anticipation, about designing for the unseen. And in that logic, predator transport doesn't belong to wildlife conservation or animal control. It belongs to the world of industrial engineering. Stress doesn't roar. It accumulates, and inside the narrow corridor of a steel crate, it becomes biochemical. Every transport operation involving apex predators begins not on the road, but in the bloodstream, with the slow, invisible rise of cortisol, the hormone that turns vigilance into panic. During loading, even before a single tire begins to move, the predator's body is already reacting to stimuli we often ignore: the scrape of a metal ramp, the scent of synthetic fabrics, the distant murmur of a human speech. Each of these becomes a signal, and in a closed space, signals compound into pressure. Some of the most revealing data in predator logistics comes not from claws or cages, but from hormone charts. In tests performed during loading operations, cortisol levels in lions and leopards can spike within seconds of visual contact with human silhouettes. Even if those humans are trained, silent, and non-invasive, stress does not require contact. It only requires perception. And once the animal perceives risk, the body primes for conflict. The problem is, in transport, there's nowhere for that energy to go. To reduce this invisible cascade, engineers and wildlife specialists have turned to tools that seem more at home in aerospace hangars than savannas. Visual occlusion panels, matte finish barriers that block movement and light variation, prevent the predator from seeing the activity around it. White noise emitters cancel mechanical vibration and engine hum. olfactory desensitization chambers, where the animal is gradually introduced to the transport's interior scent profile days before the move, help neutralize the shock of new environments. Together, these elements create a sensory buffer, an interface between the animal's mind and the chaotic human world it's being asked to cross. Still, numbers tell the most dramatic part of the story. In a study tracking sedated leopards, those transported in standard open-design trucks showed a 47% increase in norepinephrine, a neurochemical marker for stress-related arousal, compared to those moved in padded, insulated crates with compartmentalized interiors. In other words, even with tranquilizers, the environment dictated the animal's internal storm. Sedation, it turns out, doesn't override poor engineering. It merely masks it. One team in Namibia learned this the hard way. Over multiple transports, they noticed erratic behavior, even in subdued lions. Twitching tails, pacing, sudden vocalizations. The breakthrough came not from changing the sedatives, but from redesigning the crate interiors. By shifting from flat, reflective surfaces to angled walls with diffused light-absorbent materials, they reduced optical stressors. The result? A 60% drop in sedation frequency across comparable operations. Light, not force, had been the hidden trigger. Because that's the lesson predator transport teaches us over and over. What we assume as power management is often a failure of sensory design. The claws are not the problem. The environment is. And the aggression we fear is not irrational. It's engineered into the system by accident. Sound, reflection, smell. They accumulate, not as noise, but as threat. And the question becomes, if we misengineer for lions, what else are we overlooking in the systems we claim to control? To move a lion is to move a system under pressure. Not just biological pressure, but mechanical. The integrity of that system depends on steel, hinges, and joints, all expected to behave with absolute consistency across terrain, vibration, and time. And yet, when transport failures occur, the cause is rarely tooth or claw. It is torque, it is metal fatigue, it is a latch engineered for strength, but not for endurance. Containment cages are typically designed for rupture resistance. Welded bars, high tensile frames, dual-point locks. But what often fails is not the bars themselves. It's the way they respond to movement over distance. In one study analyzing over 30 transport anomalies across sub-Saharan wildlife relocations, more than 90% of mechanical breaches were traced not to direct force from the animal, but to cumulative torsion on hinges and latches during long-haul motion. The stress doesn't announce itself. It flexes. It grinds. It eventually slips. The response to this challenge didn't come from wildlife science. It came from freight logistics, specifically from the coupling systems used in rail transport, magnetic induction locks that activate only under precise force vectors. These systems don't rely on bolts or friction plates. They respond to electromagnetic fields triggered by motion thresholds. Applied to predator cages, the effect is transformative. The lock engages only under linear stress, resists torque, and maintains structural alignment over hundreds of kilometers, even in off-road conditions. A comparative field test between standard bolt-secured crates and magnetic induction locks yielded striking results. In rugged terrain, transport spanning 450 kilometers, traditional latches showed measurable wear and minor displacement after just 120 kilometers. The magnetic systems, by contrast, maintained structural fidelity across the entire journey with zero need for mid-route inspection. In engineering terms, it's the difference between a sealed vault and a reinforced door. Both protect, but only one is built to endure. And still, the consequences of a minor failure can echo far beyond the crate. In Botswana, during a late-season relocation effort, a leopard escaped a transport unit after a rear latch loosened under terrain-induced torsion. No one was injured. The animal was recovered. But the breach revealed a silent oversight. the underestimation of kinetic stress. The design had accounted for strength. It had not accounted for fatigue. That is the paradox of predator transport. We prepare for the visible threat, for claws, for muscle, for the unpredictable nature of a confined predator. But we often ignore the predictable degradation of the machine itself. We over-design for ferocity and under-design for physics. And in doing so, we misplace our trust, not in the animal, but in the infrastructure that surrounds it. Because a lion may resist, but steel will always yield to repetition. And the true engineering challenge is not in locking the door. It's in making sure the door still holds after 300 kilometers of vibration. There is a silent frontier in engineering. It doesn't announce itself with alarms or flashing lights. It appears when systems designed for structure encounter systems governed by instinct. When cages are no longer just about resistance and bolts are no longer enough. In predator transport, the real complexity begins not when the door is locked, but when the wheels start to turn and every vibration becomes a question. Will this hold? And more importantly, will this translate? Because what is being transported is not passive. A lion in a crate is not cargo in the traditional sense. It is a biological engine, alert, adaptive, and potentially volatile. Its responses are immediate, internal, and often invisible until it's too late. It doesn't just react to failures. It responds to signals, changes in temperature, frequency, airflow, rhythm. The margin for error is not wide, and the systems that contain these creatures are not truly safe until they learn to speak the same language as the animal's nervous system. That's where the limits of traditional containment logic reveal themselves. Most transport engineering follows a linear progression: heavier load, stronger structure, more risk, more redundancy. But in predator logistics, redundancy doesn't always translate to reliability. A thicker steel wall does nothing if the lion inside has begun to overheat. A triple lock latch means little if sound reverberation in the crate triggers a fear response. The danger lies not in failure, but in misalignment between what we build and what the animal perceives. This is why modern wildlife logistics is turning toward adaptive systems, machines that no longer impose conditions, but respond to them. In South Africa, for instance, a wildlife transport firm has integrated motion feedback technology originally developed for the pharmaceutical cold chain. These systems were designed to keep high-sensitivity biological samples stable during international air freight. Now, they serve lions. The crates are embedded with multi-axis accelerometers and AI-guided dampers that respond in milliseconds to changes in terrain. The result isn't just a smoother ride. It's a reduction in the animal's stress cycle, fewer spikes in cortisol, fewer signs of panic, and in some cases, the complete elimination of sedation. That shift marks a deeper change in logic, the transition from passive containment to predictive management. Engineers are no longer designing for restraint, but for compliance. For conditions where the animal's nervous system remains stable, where its fight or flight reflex isn't activated because nothing in the environment tells it to be afraid. And that requires a different kind of intelligence, a mechanical empathy, one that maps not only the load, but the load's perception of the world. But perhaps what's most revealing is how this niche operation, the relocation of apex predators, exposes vulnerabilities in much broader systems. It forces a question that reaches beyond wildlife. How often do we mistake control for stability? In predator transport, the illusion of safety is the most dangerous feature. A locked cage feels secure, but if that cage amplifies noise, or reflects light, or vibrates out of rhythm, it becomes a source of pressure, not a barrier to it. The same principle applies in agriculture, in freight, in urban infrastructure. The failure isn't always mechanical. Sometimes it's perceptual, and those failures often remain invisible until their consequences are unavoidable. That's what makes predator logistics so fascinating. It's not the drama of moving a dangerous animal, it's the discipline required to do so without confrontation. The shift from physical force to cognitive modeling, From brute strength to systemic understanding, from making something stay to making something stay calm. In this sense, predator transport becomes a metaphor, not for danger, but for complexity, for the challenge of building systems that acknowledge what they carry, systems that listen, that respond, that learn. Because fear is not an external hazard. It's a process, a sequence of environmental inputs. And when engineers begin to map that sequence, to anticipate it, to adjust for it, they don't just protect the animal, they protect the mission, the people, the system itself. So the next time we imagine engineering as the triumph of steel and horsepower, it's worth remembering the quiet operations, the ones that succeed not by overpowering nature, but by respecting it, by understanding that a predator in motion is more than a body in a box. It is a test of how far our machines can reach into biology and how far our systems must stretch to accommodate perception, instinct, and fear. And in that narrow space, between the tremor of a crate and the silence of a stable ride, we glimpse the future of intelligent logistics. One that doesn't just move life, it moves with it.